Okay, last time we showed a little bit how we can, first we talked about how to simplify the system of force. So what we did was that if you have a system of force, how can I bring them all into the single point and reduce them into a single force and single moment. Then later on says that we want to simplify it even more and simplify the entire system to a single force, get rid of the moment as well. So we'll look at it in theoretically how we can do that, so we're going to look at it how we can do it in an example. So example 4.17. So this is how it's been like this. And then mark here. Right here. 1.5. Here. 0.4. Over here. And then you have forces. And moments. So we have 4. Or kilonewton here. And then 8 kilonewton here. And 15 kilonewton meter here. Okay, so that's the problem we have. So we have two forces and one moment, and then what we want to do is that we want to reduce these two force and the moment to a single force. Remember in the previous example, we reduced them to a single force and a moment. So in previous example, for example, I said, let's bring them all at point O. So it would be one force, one moment, if I bring everything at point O. Now I will say that I don't care where you put it, I only want to have one force. Okay, so that's all I want. This time we are free to move it around, but we want to have only one force. So to do that, again, the very first thing we are going to do is that we have to find all the x and y component of that any force in there. So the 4 kilonewton is already in the y direction, so we don't need to do anything. But this one we have to, the 8 kilonewton we have to find, so it has a 3, 4, 5. It's like 3, 4, and 5 at that triangle. So if I draw that, and if I call these alpha, so the cosine alpha would be 3 over 5. So the cosine alpha would be 3 over 5, and the sine alpha would be 4 over 5. So I can go ahead and find the component here. So I have two components here. one is going to be 8 kilonewton times the cosine alpha. Cosine alpha is 8 kilonewton times 3 over 4. And then I have the vertical component there, which that right here is going to be 8 kilonewton sine alpha is going to be 8 kilonewton over 5. So these are the two forces. Now I have everything in the x and y direction. The next is I'm gonna do is that I'm gonna add all the x component together, all the y component together, all the moments together. So let's go and do that. So sigma fx, add all the x together. Because these components I don't have anything else, so it's gonna have the 8 times 3 over 5, 8,000. 8,000 times 3 over 5. So that's the sigma x I have.
4,800.
So 4,800 Newton.
Newtons, yeah.
And then the sigma fy. So in the y direction, the 4,000 is going down, so it's 4,000 going down. And then I have the 8,000 times 4/5 going up. So that's 4,000 negative and positive, and should gives us 400. So it's 2,400 units. So that's the sigma fx, that's the sigma fy, and sigma m is just one of them, so I don't need to do anything what. So Fr, the resultant force, would be Fx squared plus Fy squared, which would be 4,800 squared plus 2,400 squared, which gives us 5,372 meters. So this is the resultant force. Next, okay, what's the angle of that resultant force? It's going to be tangent inverse of sigma fy over sigma fx, tangent inverse of fy, 2,400 divided by 8. So, which gives us 26.6 degrees. So now I find the sigma fx, sigma fy, and fr. So if I go ahead and say, I want to make that equal to this, so if I redraw that again. So I know that the sigma f is 4 to 8. Assume it's going to be, for example, somewhere. This is the 48. And then sigma y is 24. 24. So the fx, sigma fy. And then I know that, okay, the fr will be that. So that's the fr. And that's it. 26 degrees. The angle is also 26.6. So that's how it is. Right? So it's a sigma fx, sigma fy, fr, and then. But I want to make that equal to this. At the moment, are they equal? No, because there's actually we have the moment there. The moment is already there, and those forces also had a moment initially. There. And now I want to replace that the moment that I created right now, whatever it is not going to be equal to that. So the point is that I have to play with this back and forth until the moment it creates become equal to moments is available. So one more time. Previously what we did, we bring all of them to one point and then we compensate for the moment. Either we add them or subtract. Now I don't want any moment. Now I just want to have the force. How to get that? I have to start playing with the force until that force itself compensates for the moment. So how to do that? First I have to see how much moment I have there. So if I go there and say originally, so if I call it the case 1, originally how much moment I have there. So the sigma n at case 1, how much it was that? And considering counterclockwise positive. Yes.
I think it's saying clockwise is positive, so there's got to be a negative 15.
When we add it as a negative.
Okay.
Because we can consider them and remember as a negative. Or we can do it the same, get the clockwise positive and then do that. So this to do that, the sigma for the for case 1 or case 1, sigma m about point O. I'm going to calculate all the moment about point O, considering the counterclockwise positive. I want to see how much. So the first one I have is the 4,000. Newton. So it's going to be 4,000 Newton. And the distance is 1.5. And this is about O. It's going counterclockwise, so it's going to be positive. The next one, I have these two forces. So first I will write maybe the vertical one. So it's going to be 8,000 or 8,000 times vertical one is 4, 5. That's the force, the vertical. And the distance is 1.5, 1.5, 1.5. 1.5 plus 1.5 plus 1.5. That's the distance. And it is rotating about the point O. It's going to be clockwise. So this, the first one is going to be negative. Second one is going to be positive. That is fourth one and go clockwise, so it's going to be negative.
That way is counterclockwise though.
Which one?
Yeah. So. First one's on that.
First one clockwise negative.
Oh yeah, it's around 0.0, yeah.
The second one counterclockwise positive. The third one
Yeah. So
is that the horizontal one, so it's going to be 8 times 10 to the 3, so 8,000 cubes. So this one, and the distance is going to be 0.5. Distance is going to be 0.5. Again, about 0.0, if I bring it here, it will rotate the clockwise. So it's going to be negative. And then, don't forget the last one, which is that. And because we assume here, because we assume the counterclockwise is positive, so this one is going to be negative. So you see, I should put the negative sign here, because we assume the counterclockwise function. So this is the total moment I have originally. So originally, before I'm doing anything, that's the total moment I have. Which I don't have it here. Do you have the value for that?
I got 5,400.
How much is it?
Yeah.
5,400 Newton meter. So that is for the case one. So I know that originally at 1.0 I had that much moment. Right? Now I have to have the same amount of moment here. I have to make sure that I'm going to get the same amount of moment here. So I'm going to do that. I'm going to say for the case 2, calculate the sigma moment for the case 2 at what 0.0, consider counterclockwise positive, equal to, so the horizontal one passed through the 0.0, doesn't have any moment. The vertical one doesn't pass through, so it has a moment, so it's going to be 2,400. Now, what's the distance?
We can just choose, or we have to figure it out.
You have to figure it out. That's the thing. We want to see where we should put it, so it gives us the same moment I have it here. So I don't know where it is. I'm gonna just say I don't know where it's gonna be. Wherever it is, assume the distance d. I'm gonna say multiply by d, and the moment is counterclockwise, so it's gonna be positive. Now I have that the moment here and the moment here should be equal. So these two cases should be equal, correct? So I'm saying that if I point, this is for the case 1, this is for the case 2. So the sigma m about O for the case 1 should be equal to the sigma m about O for the case 2. So it's going to be, tell me that 5400 should be equal to 2400 times D. Then the D would be so
1.25.
yeah, so you have 2.25 meter. It means that if I put that resultant force at 2.25 meter from the O, then I don't need to have any moments there. Or in other words, I reduce the two forces and moment into a single force. Right? Any questions? So let's look at another example.
4.8 or 4.19? 4.18.
No, 4.18.
Alright.
So since I assume we have uh, frame like this, and there are two forces at one. That one, two forces. The one force is here, which is 175. The other 4, 5, and then again it's alpha, and then 3, 5, and 6. Five. Here's gonna be 3, 5, 3. So it said if you have forces like that applying on that frame, so you want to reduce, these are the 3 forces, want to reduce it to the single force, no moment. So similar to previous one, first we have to go and find all the sigma fx and sigma fy. To do that, again, I have to find these 2 components here. This one, this one. And to do that, I need that angle. So, again, cosine alpha would be 4/5. And sine alpha, 3/5. So, if I go ahead and say, okay, these 2 forces, this one is going to be 250 cosine alpha, 250 cosine alpha is going to be 250 250 and 4/5. And this one is going to be 250 sine alpha, and 250. Agree? So now I go ahead and find the sigma of x and sigma of y. So I go ahead and say sigma of x would be the x direction. I had minus 700, 175, and then the minus 250 pure 5. Nothing else in there. Y x direction. So it comes out to negative 325, yeah. Then the y direction and all the one in the y direction, both of them pointing down, so both of them are negative. So it's negative 60 minus 350 4/5, which would be negative 260 count. Same as before, the Fr, the resultant force, is Fx squared plus Fy squared, which would be 325 260. Would be 460. And the angle it has is theta. So we tangent inverse of y over sigma of x. The inverse of sigma of y. up to here, like the previous, 6.x, 6.5 resultant force. Now I want to replace them, so now I have that. But I want to replace that in a way that I'm not gonna get any moment, only with a single point. So, in other words, I want to say that I want this to be replaced with single force. That's going to be these two. Where it's going to be, I don't know. So, assume it's going to be here. It's going to be 325. And it's going to be done on 260. And the resultant would be this, which is bar 416, and the angle is 38.7. The question of the year. No, it doesn't say that the problem, if you read the problem doesn't say that find the point that is going to be only one force. It doesn't say go ahead and replace that with a single force. It says go ahead and replace it with the one force here on the vertical part of the frame. It doesn't word it like that, but it is what it wants. So replace it with a single force on the vertical part of that frame. It says, what it says where that single force will be hit the AB. So if it's the AB, the question is that if I replace that with a single force, where that single force is going to hit the AB. In other words, just replace that with the force on the AB. So this is not what it's asked, this is what I found, but this is not what it's asking. It's asking if this is the AB, where on the AB that force is going to be. The problem is that if this is, we call this C, I call C, we don't know where on the BC it is. We don't know where is it. I know it's probably somewhere on the BC, but where on the BC we don't know because we want to make sure it's going to have the same moment. So one of the how to handle that is that one thing I can do, I can move the force along the line of action. So one thing I can do is that I said I'm going to draw the line of action for this force and assume it hits it here. We don't know if, but assume it hits it there. I'm going to bring the FR to that point. I will put the FR there. From there, I will bring it here. And then I will bring its component as well. So it's going to be 260. It's going to be 325. Agree up to this point? So basically what's happening here is that this will not. So this is going to be equal again to this. So if I bring it, I just draw, I'm not drawing that part, but bring it down here. this is what I have a single force here, Fr, 260, and 325, and that's the point A. Because I brought that from here to here. Got it? I brought it from here to here. So now this is what I have. Any question up to here? What happened? So I reduce it to the single one, and then I bring them down here. It gives me this. Now I want to see, okay, where it's gonna be here on the AB. It is on the AB right now, but where on the AB? That's the part that I have to make sure the moment the FR created is going to be the same as the moment these three are created. That's the only way that they are going to be equal. So I have to go back and set the original case that I have and say, assume this is my original case 1. So I said, for case 1, I have to find the moment. So I have to find C. You can find it about any point, it doesn't matter. You can pick any point you want. Probably A is the easiest one, so you go ahead and say sigma m about point A, for the case 1, would be 175 times 5, and it's going counterclockwise, so positive. Then I have this 60 times 3, so it's 60 times 3, and then it's going clockwise, so it's going to be negative. Then I have this one, the vertical component of that, so 250 times 4/5. This one. That's gonna be 8. 3 plus 5. And again, about A is gonna be counterclockwise, so it's gonna be, sorry, clockwise, so it's gonna be negative. And then the horizontal one here, so it's gonna be 250. So it's gonna be 250. And the distance is 6 plus 5. And again, it's counterclockwise, so it's going to be positive. So, counterclockwise, positive, and 650. Is that right? So that is what I have for the case 1, and then I'm gonna have, if this is the moment for the case 1, I should have the same moment for case 2. So I'm gonna have the sigma n, the both point A, and assume this is the case 2, or I will call it the 3. So where's going to be that force hitting the AB? I don't know, so I just assume that distance to be D. I don't know where it's going to hit it, but assume it's D. So I'm going to say that the moment, the vertical one passed through the A, it doesn't have any moment, that 325, 25 is going to be times D, and it's going to be counterclockwise or positive. So these two should be equal. So if I go ahead and say sigma m about A for the case 1 should be equal to the sigma m about A second case. And if you do that, gives you the D equal to 2.29. If they ask where it would be on the BC, it's the same thing. So you just consider this distance D and write that and find the D. Question? So that's how we reduce system of force or moment to a single force. That's the simplification of the force and moment. The next part of it, the last section of this chapter, is a very short section, but it's going to be really, really important section because we're going to use them in many different courses a lot. And that's the distributed load. So far what we had was like, assume I have a B, and then I have a single force applying on it. So it's a single force applying on some point.
Say that again.
A single force applying on a point. But let's consider a couple of examples. For example, if there's a ocean, and then there's going to be a submarine under that water, where the force is going to apply on that. If you look at that submarine, every location on the surface, if you look at the surface of the submarine, can you find any location that the water does not pressure it? So every point on that surface that you look at it, there is going to be water pressure. So you are going to have the force applying on that on every single point. So it's not that you have a single force. No, in this case, you are going to have forces applying on every location of that. Every point you can find, you are going to have the force applying on it. And on proper here. So this is not anymore a single force. You have a load applying on the entire object. Another one that problem that you might for example, look at that table. If I have a table, the air pressure on that table. Again, if you look at the surface of the table, the air pressure is equally available on every point on that table. There's not a single point that says, okay, there's a force here and there's nothing else works. So again, if you look at that, you're going to have the air pressure applying on that surface anywhere that you look at it. So, unlike the first case that we discussed it up to here, that you have the forces applying on a point, now you're going to have forces that apply on the area or the entire surface. So that's going to be distributed load. So, any question about it? What does it mean or what it is? In other words, it's easier the pressure, anywhere you have a pressure is a distributed load. You have it on every location of that object that you are studying. Now the problem is that how am I going to work with that or with that? How do I analyze either of these two? This can't be done. So when you have the distributed load, to be able analyzing distributed load, we need to replace the distributed load with a single force. So, to work with that, there's no way that we can analyze the distributed load the way it is. How we can, up to here, we learned that, okay, we can do it if it's a single load, but we don't know how to do it. So if you find a way to reduce this to that, then we know how to analyze. So the entire method is that if we have a distributed load, we have to go ahead and replace that with the single force. That's what we want to do. So if I want to find if I want to replace it with the single force, what should I know? What should I find? So I have to find, so we need to find two things. First, the magnitude of the force. So the first thing that we need to find is the magnitude of single force. The second thing that we need to find is the location that the single force will be applied. The location of the single force. Applied. So if I want to change that to the single force, first I have to know how big it is. Second is that where it is. Where I can replace that, but where I'm going to put it. So two things. First of all, replace it in sync. Replace it. Find the magnitude, and second, the location. Other word. So for example, if I have something like that, and there's a distributed load on that object, I want to say, if I want to say, okay, it's going to be equal to single force that I have to find this magnitude and that location. So I have to find how much is F and where is the location I'm going to put that. So you got it up to here what you want to do. Yep. So there are two cases that we can work with that we don't do much 3D, but I'm gonna just show you. If it's a 3D flow, if we are dealing with a 3D case, so I have a code like that, and there's gonna be the 3D force applying on that force. So I have these 3D forces applying there, and I want to say, okay, I want to replace that with a single one. So I want to go there, say, okay, there's going to be a single force, and how much is it going to be? So that single force is going to be that. The magnitude of the F in the 3D, F, the magnitude of that is equal to the volume of the load. So, how much is the volume of that load? Whatever is the volume of that load, the magnitude is going to be the volume of that load. The location, so that's X bar, Y bar. The location would be the centroid, the location of the is the centroid of the 3D load. X bar is the centroid of the 3D load. So, for that, just know that we are gonna switch to 2D. We are not doing the 3D. But in the 3D, just know that the magnitude of that F is just this volume of that volume of that green part. whatever that volume is that F, and the location is that where is the centroid of that volume? It's going to be right at the centroid of that volume. But let's look at the 2D case that we are going to work with that board. That if I have that in 2D, there's a zoom, and there's a load here. So again, I want to replace that with single force, and that single force is going to be applied somewhere here. If that is, this one is Wx, load Wx, the magnitude of the F is area of the load so how do you calculate the area of the curve? If I go ahead and say, hey, that's going to be the x-axis, and that's going to be the Wx. Then the force would be integral of this is the area under there, the area under the curve is the integration, right? So that's going to be the area of the load. Where is going to be the location? At the centroid of that. So if the centroid of that is located here, assume for example that's it. This bar, and that's the y bar. That passes through that centroid. So that distance is going to be x bar. So it passed through the centroid of the area. So x bar is the centroid of load, and x bar would be here this to remember it word. The previous question, if you Wx dx replace it with dA, this one. But usually it's easier this way. So in general, so that's how very quickly if you have a distributed load, we want to replace it with a single load, and we have to find its location. In the 2D case, the magnitude is the area under the curve of the load. The location is the centroid of the load.
Okay, say what the centroid is again? What's the centroid?
Central area.
Oh.
By the way, you don't care about the y because you can move it up and down. It's a line of action. You can move it up and down, doesn't matter. You just care about the x.